Who was asking the derivation part?
So what is the difference between A and AF? Means
A and FF. AF.
yes, sir. A and AF.
If the voltage gain
Open
with
loop,
feedback,
open loop gain and
That
feedback.
voltage gain with feedback.
this again. Okay, this I am telling you. But also, what you should do, you should follow up the class and you should try first yourself to understand it. Okay. Only if it is in your mind, if you throughout the class, if you sincerely follow, then already I mentioned, and it is not so difficult, and there is there should not be any confusion on this. What is AF and what is AF? If you consider simple one basic amplifier, that is in under open loop condition, that open loop means is output and input does not have any connection. Okay, so output and inputs are open. Then if you apply a signal, say xi is the input signal, output signal is x0 and gain is a, then we can simply write x0 is equal to uh, x0 equal to simply what
A into
it
Xi.
is. Yes, we can write simply x0 is equal to a xi, or simply a is equal to x0 by xi. Okay, this is simply input output relation. Whenever a part of the output signal is fed back through some network, feedback network, it is called feedback network, to extract a part of the output signal information. This signal may be voltage or current. Accordingly, this feedback network is configured. Okay, and this part is XF, and this is XF. This is here connected to one comparator. Here it is plus, here it is minus. Here now it is XS, and this is XI is the input signal to this. Under such configuration, what would be the gain? Overall gain. Actual input is Xs, output is X0. Here it is not simple Xi, and Xs is not equal to Xi, whereas now Xi is equal to Xs minus Xf, where Xs is the externally applied source signal, and Xf is the feedback signal which is coming from the output. Under this configuration, what would be the gain, overall gain? That is what AF. AF is the gain with feedback, and A is the basic amplifier gain under open loop condition, that is without feedback network. So, and that we derived AF is equal to 1 plus A beta. Okay. So now it is clear to you.
Yes, sir.
So hopefully this problem you can solve. If the input voltage and voltage gain of open loop feedback amplifier are 5 millivolt and 100, okay.
Sir, one
Uh,
small.
uh-huh.
Yes, sir.
Sir, why is XS equal to XI plus XF?
Why xi equal to
XS
Negative
equal to
feedback.
XI plus XF.
x xi
With
equal
feedback.
to xs minus xf, I have written here, and here xs equal to accordingly xi plus xf. That is also I told you the two types of feedback. One is positive, another is negative. That this feedback signal, whenever we are applying to the input, that may be additive, that may be subtractive. That means that may increase the overall input signal xi, or that may decrease the overall input signal xi. So if it is decreased, then it is negative feedback. So we are considering here negative feedback. For positive feedback, it would be xs plus xf. That means we can write
Okay, sir.
xi as xs plus minus xf. Either it can increase or decrease. Accordingly, we can write this. Okay, so I am not going to solve this problem as it is a simple problem, and this is the by using a simple formula that already I told you can solve. So hopefully you have gone through this, and any one of you have solved it. Can you solve it?
Yes, sir.
Yes.
Yes, sir.
Okay. So that means just those who are not able to follow up, just here for them, A is given as feedback, and this is open loop gain. An open loop feedback amplifier. The gain of an open loop feedback amplifier, right? So that you should remember. Open loop, that means here the gain of this amplifier, basic amplifier under open loop condition. A here. And that A is given here 100. The input voltage is given as 5 millivolt. That means Vi is equal to 5 millivolt. Feedback factors, that is beta, is given by 1 by 50. Okay. So then what would be the output voltage? So output voltage of the feedback amplifier, note it here. So that means under, if
10
we
millivolt.
provide, okay, if we provide this or the connect this feedback network from the output to the input, then what would be the corresponding output voltage for the given input voltage? Here, the input voltage Xs, the Xs that is given by 5 millivolt. What would be X0 with feedback factor beta is equal to 150? Okay, so that simply you can calculate AF is given by YA divided by 1 plus A beta, and accordingly you can calculate the corresponding output voltage with feedback X0F, that is given by AF XS XS. Okay, and accordingly you can calculate the output voltage.
Sir, if nothing is mentioned in the question, we'll assume it as negative feedback.
Okay, that is very good thinking. So in that case, if it is not mentioned, then what you can do, you can take either positive or negative, it may be the case. Accordingly, you calculate the both the cases and calculate both the voltage gain for the cases also, for both positive as well as for negative voltage gain. Okay,
Sir,
negative feedback.
since here X source, this one is a voltage source, so we are taking excess. If it was a current one, then we have to take the current one that is going through the feedback amplifier, right?
Yes, definitely. If it is voltage, then it is voltage, output voltage. If it is current, then it is current. Also, if the input is current, output is voltage. Also, that also can be. And if input is current, output is voltage, that also can be possible.
So then what
So,
we will take here, negative or positive?
uh-huh, uh,
So what we
yes,
will take here, negative or positive?
hmm. Negative or positive, once you take the A beta as positive, another A beta is negative, and calculate the overall AF. For A for positive, it would be negative feedback gain. A for positive, it would be positive feedback gain. And accordingly, you calculate the output voltage for negative feedback gain, negative feedback output voltage for positive feedback. Okay. And accordingly, you mention that if the feedback type is positive, the output voltage would be this. If feedback is negative, feedback type is negative, then the output voltage will be this. Just you mention. And if specifically it is mentioned, then you have to follow according to the feedback type. Okay. Take care. So then we are moving to the next topic. These are the reference books which you can follow. Also, it is given in details from the in the website, the detailed syllabus as well as the reference book. So you can go to that also. In the website, you go see you can see go to the electronics department and download the UG syllabus. There, the first year basic electronics ECC01 you search and you can find the detailed syllabus there. And also you will find all the reference textbooks and the topic-wise syllabus. That's why I have not shared here the syllabus as it is available in the website. Okay. So now let us come to this point, the effect of negative feedback on the performance of the amplifier. What we are I told you in the beginning of discussing this different types of feedback, the positive and negative feedback. I told you that negative feedback has several advantages. That though it reduces gain, but it has the several advantages. So what are the different advantages? Now let us see. First of all, if we see the gain, if we see the overall gain with negative feedback that already we got is given by 1 plus A beta. So as you can see here that in the denominator term, this 1 plus A beta, 1 plus A beta, which is greater than 1, this indicates AF less than A. So it indicates that the overall gain of the amplifier with feedback is less than the gain of the amplifier without feedback. So this is just one drawback in negative feedback. It just reduces the gain. Okay. But what others? Now let us see what others the advantage we can get. We can realize with negative feedback. The gain stability, again, if we follow the expression for the overall feedback gain with negative feedback, that is given by AF is equal to A divided by 1 plus A beta. Again, for your convenience, let me define this A as the gain of the basic amplifier, that is without feedback. This is basic amplifier. Say this may be any feedback amplifier where the feedback network is not connected. And this is the gain when the feedback network is connected to this amplifier. From its output to the feedback network, it is connected to the input of the amplifier. And this may be one comparator or simply a mixer. This is a mixer or comparator. Okay, comparator. Comparator for the negative type feedback. Negative feedback, what would happen? It is excess, it is except, it would be plus, it would be minus. This indicates that it will be having the 180 degree phase shift. That means it will reduce the, it will superimpose with the input signal in 180 degree out of phase. Accordingly, the overall input signal that will be reduced. And this is a mixer for the case of positive feedback, just it will be added with this, and that means it will be mixing up the axis and feedback network, the input feedback signal. Okay. So now here, generally for feedback amplifier, the gain A is such that A is very, very greater than beta, or A is greater than beta generally. At least A is greater than beta. If it is, then A beta is generally very, very greater than 1. Whenever we'll use the amplifier and feedback will connect a feedback network, we make A beta such that the A beta is very, very greater than 1. In that case, AF is equal to A divided by this 1 plus A beta. When A beta is very, very greater than 1, then 1 plus A beta. This we can approximately write as A beta. So then we can approximately write here as A beta and A approximately equal to. And in this case, A beta, A is given by 1 by beta. So what you can see here, that this overall gain of the amplifier with feedback does not depend on the amplifier gain, whereas it depends on the feedback network. Okay, that is the feedback factor. Feedback factor basically depends on the feedback network. Now, if we make the feedback network a stable feedback network, which does not depend on any environmental changes, then the overall gain of the amplifier with feedback is stable, more stable. As the amplifier basically a semiconductor device, or its amplifier gain may fluctuate with change in the environment or change in temperature. Okay, but these changes can be avoided by including a feedback network and by making it more stable. So that indicates that the gain of the amplifier is stable. So that is what one advantage is. Though the gain is reduced a little bit with sacrifice of this gain, which can be further increased. Okay, but gain stability in the gain or the stable system can be realized. Next is the distortion. So this is one for the gain. Distortion is what do you mean by distortion? Do you understand it? What do you mean by distortion?
Yes, sir. Some unwanted signals come in between from the external environment. That
Disturbance.
input thing.
No, this is what disturbance or noise. Say for example, sometimes during our class, someone is unmute their microphone and some others surrounding noise come into this lecture times and create some disturbance or noise. This is the unwanted signals, and this is what not distortion, this is disturbance, right, or noise. Distortion. Distortion is something, suppose you have purchased one showpiece, right? Somehow it is distorted or it is broken. Or what you wanted, that is somehow it is not as per your expected. So that is distorted. Okay, this is what distortion. So this distortion means here, suppose if you consider this is our amplifier A, the input signal is Xi, the output signal is X0. So the amplifier gain, its A is constant what we consider, and accordingly we should get X0 is equal to AXI. However, this amplifier gain is not linearly related with X0. Will you agree with me? Because if you consider the transistor characteristics, if you consider the diode characteristics, these are not exactly linear. It is, whereas it is a non-linear. All of it, do you know, you already you have seen the diode characteristics, how it changes, diode characteristics.
So for a small period of time, it increases linearly. Then after the knee voltage, it exponentially increases.
So this is what the diode, actually diode equation is the exponential equation. Hey, unmute it. Unmute. All of you should unmute yourself. Whenever you will talk, then you will. Okay. So this is one exponential expression. It increases exponentially. So after the knee voltage, you have right. Not after the knee voltage. Just you can approximate it is as the linear, but it is not exactly linear.
How it is increasing exponentially?
Which one?
This graph.
This graph, what I am drawing here, this graph is for what I told. This graph for what? Which graph is this?
Sir, it is the forward bias characteristic of a diode.
Good.
IV graph.
That I told you. This is a diode characteristic. So diode characteristics follow the exponential expression. That is the relationship between V and I is exponentially changes. Okay. So and also do you know the expression for the IV characteristics? Do you know the expression for the IV characteristics?
Oh, sir.
I equal to I0 into
E power minus
E की power QVD by KT minus
by
1.
K minus 1.
good. So I is equal to I0 into exponential
QVT
V
V by K, VD by
by
KT
KT minus 1.
by KT minus
minus
1.
1.
Okay. So now if you increase the voltage, this is the forward bias voltage. If you increase voltage, the Q is the electronic charge, K is the Boltzmann constant, T is the temperature. So as you can see, it related with the temperature also, and it is increases exponentially, right? So that's why it increases exponentially. So similarly, for a transistor also, transistor is a junction of two PN junction diode. Also, it follows the exponential relation, that means non-linear. So it is not exactly the linear relation, it is approximately linear relation, and sometimes it comes into the nonlinear region, and due to that, if you apply a sinusoidal signal, a sinusoidal signal means this is the waveform. What if you apply the sinusoidal signal at its input for distortionless amplifier, at its output, the amplifier should provide the signal with amplified versions of the input signal. That means it should replicate the same waveform, just with its magnitude is magnified. Okay, or the amplitude is magnified. Are you getting it?
Yes, sir.
Okay.
Yes, sir.
But due to nonlinearity, what happens? If it come into the cutoff region, or if it goes into the saturation region. In both of the cases, it does not provide, or it cannot provide the exact reproduction of the input signal. Sometimes it is distorted. So it does not follow the exact sinusoidal waveform. That sometimes from the top portion it is clipped. From the bottom portion, it is clipped if it is beyond the cutoff region. If it is beyond the saturation region, it is clipped. In that way, exact sinusoidal signal you may not realize. And also, it may not follow the exact sinusoidal waveform. Rather, somehow it may be distorted. Okay. So that is what distortion. This distortion can be reduced with negative feedback. Say for example, if you consider the distortion without feedback is given by, for the given input signal xi, whatever the distortion, that at the output the distortion is d, okay, without feedback. Then with feedback, actually the gain, overall gain AF is given by A divided by 1 plus A beta. So accordingly DF, that is reduced by the factor 1 plus A beta. Okay, so that's why DF is equal to D divided by 1 plus A beta. This is what the, as you can see, this distortion is given by distortion for the case without feedback, and this is the distortion with feedback is reduced by the factor of 1 plus A beta. Okay. So this is what is distortion in amplifier and how with feedback the distortion is reduced. Could you understand it?
Yes, sir.
Now for the also the noise is reduced with feedback with negative feedback. Again, if we consider the same basic amplifier, okay, of gain A, and if we consider the input noise, suppose the noise is Xn, Xn be the noise, input noise, then the corresponding output noise without feedback, that would be given by X0n. Okay, then as per the as already you told, and hopefully all of you know about what do we mean by noise. Noise is some unwanted signal which appeared, okay, which appeared in the communication system or electronic system. That is what the noise. So for examples, right now I am taking your class. From the road, the different noise is coming when the vehicles are moving, when someone is talking. So that creates some disturbance for you. Okay, so that is what the noise. So that noise will increase if I use the loudspeaker or a microphone, and if I increase the volume, then the along with my sound, the noise also will input. Noise will be amplified or increased. So that noise signal, accordingly, if Xn be the input to the amplifier, the noise input to the amplifier, the corresponding output X0n is given by AXN, right? This is without feedback. Now, with feedback, the gain is as AF, the corresponding noise without feedback, with feedback, X0NF, that is given by AF, this is noise, okay, Xn. Okay, so then AF is given by A divided by 1 plus A beta into Xn. Now AXN is already we got X0 n divided by 1 plus A beta. So what you can see here, X0n is the output noise without feedback, and X0NF, that is the noise with feedback. So what we can see that the output noise is reduced by the factor 1 plus A beta. Again, the output noise is reduced. So distortion is reduced, noise is also reduced with negative feedback. Okay. Then the input output.
Just please one more time.
Yes. Can you tell what?
What is ONF? Can you explain one more time?
X0NF is the noise whenever the feedback is connected. Suppose a feedback network is connected. Under this condition, if the same noise input is appeared, the corresponding input, corresponding output we are defining as X0NF. Under this, with this feedback connection of the feedback network. And when this feedback network is not there, then whatever the input, that is X0N. So X0N is the output noise, output noise without feedback. Okay, and X0NF, this is the output noise
With feedback.
with feedback. Now it is clear?
Yes, sir.
Now input output impedance. Similarly, the feedback network also affects its input output impedance. So there, and input output impedance is increased or decreased by the factor of 1 plus A beta. Okay, either it is increased by 1 plus A beta or it is decreased by 1 plus A beta. That means either it is multiplied with this 1 divided by 1 plus A beta or it is increased by this. Just for example, if some amplifier input is Ri without feedback, then with feedback, the amplifier input, it may be Ri into 1 plus A beta, or it may be Ri divided by 1 plus A beta. Similarly, the output resistance of the feedback amplifier, if we consider Ri and R0, here let me define it, Ri and R0, the input and output resistance of the amplifier without feedback. Okay, and similarly Ri and RIF and R0F
with feedback.
that is the input output impedance with feedback. Okay, in that case similarly R0F either can be 1 plus A beta or can be 1 R0 divided by 1 plus A beta. So what you can see that, now can you tell me for one ideal voltage amplifier, what should be the input resistance and what should be the output resistance for ideal voltage amplifier?
Sir, input resistance should be low and output should be high. So RIF should be this one divided by this and ROF will be into multiplied. Then only the gain increase.
Good. That means for ideal voltage amplifier, input should be high or low. Means for ideal voltage amplifier, the input impedance should be infinite, output impedance should be 0. Okay. Practically, it is high, and input impedance should be very high, and output impedance is low. Practically, ideally, it is infinite or 0 and 0. It's clear. So accordingly, for a voltage amplifier, if you sometimes we need to increase the impedance, input impedance, and we want to decrease the output impedance. In that case, we have to connect the feedback network in such a way that it will increase the input impedance and it will decrease the output impedance, and accordingly the feedback network is connected. So that we'll see, that is what the feedback topologies, whether it is configured in series or shunt in the input or output. Accordingly, its input or output impedance will be increased or decreased based on a series or shunt configuration. Okay, are you getting this?
Okay.
So that's why
Yes.
this in that way the negative feedback is helpful to control the input output impedance as per our requirement of the feedback amplifier. Next is the bandwidth and gain bandwidth product. It is also an important. This is this you probably this has been discussed in your single stage amplifier, that is the gain characteristics. Gain, gain characteristics, frequency response characteristics of common emitter amplifier.
No.
No,
Huh?
sir. No, sir.
No. Common emitter amplifier frequency response characteristics. It has not been discussed.
No, sir.
No, sir.
How? Should be discussed, I think. Anyway, say if we consider it is the gain. Along y-axis is the gain in dB. Along x-axis it is frequency in hertz. Okay. Now, if it's the amplifier frequency response characteristics is like this, it is a common emitter amplifier characteristic. When one is feedback network is not connected and another feedback is connected. Here, this is what the frequency response characteristics when the feedback network is not connected, and this is the maximum gain over the bandwidth, and this is the 3 dB point. If you consider this is the 3 dB point, and this is what the lower cutoff frequency, this is what the upper cutoff frequency. So if it is FL, if it is FH. Okay. So now from the characteristic curve, what you can understand? Do you know what is 3 dB point? 3 dB point?
No, sir.
No, sir.
No, sir.
Okay. So 3 dB point is the that is the half power point or 3 dB point. Whatever the value of the gain here, if it is dB, then it is just below the 3 dB point. That represents the half power point. Half power point is actually, if you calculate the half in dB, then it will give the corresponding value in dB as 3. That's why it is a 3 dB point. And or 0.707. 0.707. So for example, if you consider the voltage and the relationship between the voltage and power. Say the voltage power is proportional to V square or I square, right? Now, if at this point the power is half, then V would be proportional to if at this point whatever the power, say here the power amount of power is in a system is P0. At this frequency, that is at the center, this is over this region, that is the flat region, the maximum power of the amplifier, if it is P0, okay, then if we increase gradually the frequency, as you can see that the gain is decreasing, the gain is decreasing on its either side. That is over a certain frequency, the amplifier is working, that is the working region of the amplifier. And above the frequency, above this center frequency, gradually the gain is decreasing, and below that center frequency, the gradually gain is decreasing. So as well as the power will decrease. So then if it is decreased, so in practical application, throughout the range of the operating frequency, the gain of the amplifier or characteristics of any system cannot remain constant. So that's why certain fluctuation or certain range of tolerance is accepted. And that range of tolerance is generally considered as the 3 dB point is considered as the cutoff point, 3 dB point or half power point. That means how much less value or how much variation maximum we can accept as the allowable range. Okay, so then this is what the thumb rule, and we take the half power point as the allowable range for the bandwidth. Clear? So that's why there are two cutoff frequencies. One is the lower cutoff frequency. So FL is the lower cutoff frequency. Lower cutoff frequency. Okay. And FH is the higher cutoff frequency or upper cutoff frequency. Higher cutoff frequency. Right? And this is what the bandwidth. Bandwidth is defined as the bandwidth here is equal to FH minus FL. So this is the range of frequency over which the gain or the power characteristics, the frequency response characteristics remains flat or does not change. Okay, so this is the region where the input output relationship is linear for the amplifier. Okay, and this is known as the bandwidth of the amplifier. Clear? So far, is it clear to you? It's
Sir,
clear
can
to you?
tell what the point is below that A line?
Okay, okay. Yes. That I was before. So this is what the bandwidth. Now it is clear. What do you mean by the bandwidth, operating the bandwidth, and what do you mean by cutoff frequency? Is it clear to you?
Yes, sir.
Okay. So now, if this power is proportional to V square, and if it is P0, right? Then, and if at this point is the voltage is V0, then whatever the power at the half power point is the power, corresponding power is P0 by 2, then at this point what would be the voltage? So this voltage would become, say if we consider the voltage, corresponding voltage is say V0 prime, right? Corresponding voltage is V0 prime, at which the power is become V0 P0 by 2. So this is what as the V0 prime square, that would give the corresponding power P0 by 2. So the corresponding V0 is given by V0 prime would become 1 by root 2 P0. Okay. So then whenever we will consider the voltage, then it is 1 by root 2 times. And 1 by root 2 times is what? It is about 0.707. And if you take the square of this, or if it is half power point, that means here it is 0.5. Now if you consider in dB, then what would be the change in power? dB, it is the ratio. So ratio here, if you consider the power is P0 prime, then in dB it is written as 10 log 10 P0 prime by P0, and it is given by 10 log 10. So that is the power P0 prime in dB. That is given by this. So this is what it is given by 10 log 10,
P0 prime by P0 10.
and it is about it is about 3 dB. Okay, so it is minus 3 dB. So that's why it is called the 3 dB point, or also it is called the half power point. Also, whenever it will be plotted in voltage, then it will be 0.707. So that will remember how your axis is defined, whether it is power, whether it is voltage, whether it is power in dB. Accordingly, you have to consider this. Now it is clear to you. So whatever at 3 dB point or half power point, it is whatever the value at this maximum value, it will be 3 dB down to this, if it is in dB. Anyway, this is what the cutoff point, or lower frequency and upper frequency. And this is the characteristics without feedback. Now with feedback, what happens? With feedback, the gain characteristic, this frequency response characteristic is extended like this. Okay, like this. And here, whatever the gain, say if we consider here, the gain is EAF, that is the gain with feedback. Then whatever the bandwidth, that is with respect to its 3 dB value, it will define the bandwidth. Accordingly, we define this is the cutoff frequency with feedback, FLF, the lower cutoff frequency. Similarly, it would be the higher cutoff frequency, FHF. So what you can see now, bandwidth with feedback is given by FHF minus FLF, and the bandwidth is increased. This bandwidth is increased generally by the factor of 1 plus A beta. Then the lower cutoff frequency, FLF, is decreased by the factor of 1 plus A beta for a feedback network. And the higher cutoff frequency, FHF, this is increased by the factor of 1 plus A beta. So in its two range extreme point, you can see now FHF, this is what is increased, and FLF, this is what decreased, and accordingly the bandwidth is flat, increased. And this gain is reduced. Rather, though the gain is certainly reduced, the bandwidth is increased. And this gain and bandwidth is increased in such a way that the product of gain and bandwidth remains same. Okay. So this is what the bandwidth and gain bandwidth product, and how it affects on the negative due to the negative feedback, and the effect of the negative feedback on the amplifier.
Sir, is the effect of increasing and decreasing the high region cutoff and low region cutoff is observed, or it is derived from the beginning, or we do it, or we observe it after we have set the feedback network that the bandwidth is increased?
This can be derived. Detailed derivation is also there. A detailed derivation is not required. Just you have to remember that with negative feedback, the lower cutoff frequency is decreased by the factor 1 plus A beta, and higher cutoff frequency is increased by the factor 1 plus A beta. Okay, whenever the feedback network is connected. Those who have taken admission in ECE branch, Electronics and Communication Engineering, they will read it later on in your third semester. And those, as in first year, there are different branches are there. For them, the detailed derivation is not required. That's why I'm not going here. And it will be, in that case, then you will feel bored. You may not understand. It will take some another 2 class. Okay. So that's why I'm not going to the detailed area.
Sir, the cutoff frequency or the working frequency of that amplifier, the lower and higher.
Yes, yes. Above this cutoff frequency, this is considered as the working frequency range. That is the bandwidth. As I
Sir,
told you,
sir,
bolo.
bandwidth and bandwidth frequency.
Bandwidth and bandwidth frequency means actually bandwidth means here the range of frequency at which the amplifier can be operated without much variation on the on its characteristics. Characteristics means on its input-output relationship. Okay, so you can, if you see here, beyond this region, frequency range, the gain is
Sir?
gradually decreasing. Yes.
Sir, we have another class at 11.
Yes, so I have completed my parts. Now you go through this lecture note and recorded lecture class. Still, if you have any doubt in the next class, you may ask. Okay, and also,
Okay, sir.
also in your group, I will share some problems based on today's class. You go through this, and in the next class we will discuss, and you try to solve it. And this is the problems which I will share. You consider it as your assignment. Home
Sir,
assignment. Yes.
sir, the bandwidth frequency is the frequency at which the bandwidth can work. I mean, amplifier.
Amplifier can work. The
Sir,
range
then
of frequency.
what's the
Range
difference
of
between bandwidth and bandwidth frequency?
bandwidth frequency means actually bandwidth is a frequency range. I am over a band of frequency. Bandwidth we are considering the width. Here, this is say if you consider this is one width. Okay. This here the width means the range of frequency that we are considering.
Okay, sir.
Sir, is gain into bandwidth constant, sir?
Gain into bandwidth is constant. Look at this here, the gain is decreased, and the gain is decreased by the factor of 1 plus a beta. Okay, and the bandwidth is increased by the factor of 1 plus a beta. So accordingly, what you can see, the gain bandwidth product remains constant.
Yes, sir.
Okay.
Yes, sir.
Sir, please stop the recording also. Otherwise, the recording is going on.
Yes, definitely.
So please take the attendance.
Attendance that I do not need not to take. I can download it this attendance from here. Okay. Who
Okay,
have?
sir.
Yes, I got your attendance. At which time you attended, and at which time you left. All this I can get from here. Okay.
And sir, please share the notes after the class.
Hello, sir.
Already it is shared. Already it
Okay,
is.
sir. Thank you.
Yesterday's
Can
note
we-
already shared. You can see.